Hi, in this video we will talk about how to find the derivative of exponential functions. So there's really just one important thing to remember for this topic that will allow you to find the derivative of any exponential function. So if the function f of x is in the form b to the g of x, meaning that b is the base and g of x is the exponent, then its derivative is the original function times the ln of the base times the derivative of everything in the exponent. So what does this ln thing actually mean? Well, ln is a function that's being applied to this number b. And so another way of writing ln b is to say log b base e, where e is a special number that equals about 2.7183. And we're going to talk more about that later on in this video. So here when we say log b base e, we're figuring out which exponent can we put on e, which is 2.7183, in order to get this number b. So ln b just ends up being a constant. So let's do an example of how we can use this rule. So if the original function is f of x equals 4 to the exponent 2x plus 3, the base is 4 and g of x is everything in the exponent. So in this case 2x plus 3. So now we can just plug it into the derivative rule here. So we have the original function multiplied by the ln of the base and multiplied by the derivative of g of x, which in this case is 2. And so recall that f prime of x represents the rate of change of the original function. So I've graphed both functions here, so you can see that this original function, f of x, has a steeper and steeper slope as x approaches infinity. And so it makes sense that f prime of x is getting more and more positive as x approaches infinity to represent that steeper and steeper slope of f of x. Alright, so now let's go through 3 special cases where we can kind of take a shortcut instead of going through everything in this derivative rule up here. And so if the shortcuts make it easier for you, then that's great, or you can just stick with memorizing this one rule, because all 3 shortcuts actually come from this rule. And I'm going to keep the rule up here for the rest of the video so that we can use it for reference. So the first special case is when the exponent is just x by itself. And so if the function is b to the exponent x, then the derivative is the original function times the ln of the base. So how do we know that? Let's start with using this rule up here. So if the function is b to the x, we have the original function multiplied by ln of the base and multiplied by the derivative of the exponent. And so the derivative of x is 1, and we don't need to write multiplying by 1. So that's why the derivative becomes just b to the x times ln b. Okay, so let's check out the next special case. So here we're looking at when the base is e. And remember that e is a number around equal to 2.7183. So if the function is e to the g of x, then its derivative is the original function times the derivative of the exponent. And again, let's go through it using the main rule up here. So the original function is e to the g of x. So the derivative is that function times ln e times the derivative of the exponent. And recall how I said earlier that we can rewrite ln as a logarithm with base e. So ln e is the same thing as log e base e. So we can think, what exponent are we going to put on this base e to get this answer? In other words, e to what exponent equals e? Well, in this case, the exponent must be 1, because that's going to make e to the 1 equal e. So therefore, ln e equals 1. So we can sub that in, so everything just ends up multiplying by 1, which we don't need to write. So that's why it ends up equaling the original function times the derivative of the exponent. And the final special case is when the base is e and the exponent is just x, meaning that f of x equals e to the x. And so in this case, the derivative is also e to the x. And so I've drawn a little sketch here where I'm showing that the function and its derivative are actually the exact same thing, meaning that the y value of the original function at a certain x value is the same as the instantaneous rate of change at that x value. So how do we know this? Well, again, we can use the main derivative rule up here. So we have the original function multiplied by ln of the base times the derivative of the exponent, which in this case is 1. And recall that ln e equals 1. So we end up having e to the x times 1, which simplifies to just e to the x. And so that's why e is a special number. Because you might have been wondering, like, why is this random number e useful for the ln function and so on? And that's because e to the x is that special value of the base where the derivative and the original function look exactly the same. So now let's do some practice problems. So here we have the function f of x equals e to the x over 3. And if you want, you can go and do this on a different piece of paper and then check with me, or you can just look through the video as I'm doing it as well. So to find the derivative, we can use this rule that's shown above. So we have the original function times ln of the base times the derivative of the exponent. And we can think as x over 3 is the same thing as 1/3 times x. So its derivative is 1/3. And remember that ln e is 1. So our final answer is f prime of x equals 1/3 times e to the x over 3. And we can also do a shortcut if you remember the special case where the base is e. So this is just going to equal the original function times the derivative of the exponent, which gives you the exact same answer both ways. Okay, so the next question is to find the derivative of 2 to the exponent x plus 5 times 6x minus 1. So everything in this exponent can be thought of as g of x. So I'm actually going to define it here. Let g of x equal x plus 5 times 6x minus 1. And now we can use this derivative rule. So the derivative equals the original function times ln of the base, which in this case is 2, times the derivative of g of x. And we can do this part with g of x off to the side. So I chose to do product rule here, but if you wanted, you could first expand these brackets and then find the derivative afterwards. But to do product rule, we find the derivative of this first part multiplied by the second part. So the derivative here is 1, so 1 times 6x minus 1. And then we add this times the derivative of this. So x plus 5, and then the derivative is 6. And so then I expanded and simplified to give us g prime of x equals 12x plus 29. So if we sub that in for g prime of x, then that gives us the total derivative of f prime of x equals 2 to the exponent x plus 5 times 6x minus 1 times ln 2 times 12x plus 29. And ln 2 equals some number, but we can just write the final answer with ln 2 to represent its exact value instead of having to round a decimal. Okay, so this next question is a bit tricky because there is an exponent in the exponent. So we have 17 times e to the 3 to the x. And so this exponent in the exponent means that the function is increasing really, really fast. So I've graphed it here, and it almost looks like it's going up to a vertical line, but since it actually keeps going forever in the x direction, there's no restriction on x. So it's not going to become completely vertical, like it's not actually going to be an asymptote. It just looks like it's vertical because it's increasing so quickly. So to find the derivative, we can define g of x to represent everything in the exponent. So we're going to say that the base is e, and then the exponent in this case also has an exponent, so it's 3 to the x. So we're going to have to kind of do 2 steps to deal with both of these exponential functions. So now let's use the derivative rule. So the 17 can just stay out front, it's just a constant. Then we're going to have the original function over here. Then we're going to do ln of the base, and then multiplied by the derivative of g of x. And so we can do this off to the side. So g of x equals 3 to the exponent x. And so that's going to be the original function times ln of the base, which in this case is 3, times the derivative of x, which is 1. So this simplifies to 3 to the x times ln 3. So where we see g prime of x, we can sub this in, and we can also recognize that ln e equals 1. So then this whole thing ends up giving us an answer of f prime of x equals 17 times e to the 3 to the x times 3 to the x times ln 3. And notice that some of the shortcuts could be helpful in this process, such as to finding the derivative when the exponent is just x, like we did over here, or when the base is e, like we did over here. Because we ended up just having a lot of things multiplying by 1, so it took a little bit longer than was necessary. But it's really up to you if you want to use just this rule here, or if you also want to try memorizing some of the shortcuts. Alright, so this is the last practice problem, and I made this a bit more difficult because it has a lot of steps. But if we go through it logically, then it should still work out. So this function is x squared plus 3 to the exponent x divided by 6, and all of this is to the exponent 0.5. So first of all, we can do the chain rule. So we can bring down the 0.5 out front, everything in the bracket stays the same, and then we can do 0.5 minus 1, which gives us negative 0.5. And now we need to take the derivative of this stuff in the brackets. So the derivative of x squared is 2x, and now we need to find the derivative of 3 to the x divided by 6. So we can keep the original function multiplied by ln of the base, which is ln 3, and then in the exponent we can think about this is the same thing as 1 over 6 times x. So the derivative of that is just going to be 1 over 6. Alright, so now we can simplify this a little bit just so that it's easier to understand what it actually means. And also some teachers won't like it if you have a decimal exponent or a negative exponent. So we want our final answer to have only positive exponents and ideally no decimal exponents. So everything here is multiplying with each other. So this 0.5 is the same thing as 1/2. So we can write that as 2 in the denominator. And here we have a negative and a decimal exponent. So let's first deal with the negative. So here it's in the numerator with a negative exponent, so we can rewrite this in the denominator with a positive exponent. And remember that the exponent 0.5 is actually the same thing as a square root. So we can just take the square root of everything and have this in the denominator, and that represents the same thing as this in the numerator with the exponent negative 0.5. And then everything over here is fine how it is, so we can just leave that in the numerator. You could simplify this a little bit more if you wanted to, but I'm just going to leave it like this. And also, I thought that this equation here looked kind of crazy, so I thought maybe it's going to make a really interesting graph. But actually, the graph isn't that weird. So this is the original function, and then this is its derivative. It does not look like this crazy thing, it just kind of looks normal. And we can see this makes sense because here the original function is decreasing, so the derivative is negative. Then here there's a turning point, so the derivative is 0. And then it starts increasing, and so the derivative becomes positive. So all of that makes sense. Okay, thank you for watching. That's all for this video. And I hope this has made it easier for you to find the derivatives of exponential functions.